Hey folks, welcome back. In this video we're going to go over paper 1, i.e. the multiple choice questions from the 2016 SQA Higher Physics exam paper. Now there are 20 questions in this paper and I recommend that you try them yourself before looking at these solutions. So let's get started. Question 1 says a car accelerates uniformly from rest. The car travels a distance of 60 meters in 6.0 seconds. The acceleration of the car is... Well, notice how we're given a time, we're given a distance, and we're told that the car accelerates uniformly from rest. So we're told the initial speed is 0 meters per second. And we're asked to find the acceleration. So we're going to use equations of motion here, but in order to find out which one, let's write down suvat to begin with. So we know that s, the distance, is 60 meters. We know that the initial speed u is 0 meters per second because we're told it starts from rest. We don't know what the final speed is. We know the acceleration is what we're trying to find, and the time t is 6.0 seconds. So let's put a star next to a because that's the one we're trying to find. So this means we're going to use the equation of motion that doesn't have v in it, which is going to be s equals ut plus a half at squared. So let's sub in the numbers now to find what a is. So we have 60 equals 0 times 6.0, which will just cancel out, plus a half times a times 6.0 squared. So because that's 0, we have a half times 36 times a, so that'll be 18a equals 60, which gives us a equals 3.3 meters per second squared. So that gives us the answer B. Question 2 says a ball is thrown vertically upwards and falls back to earth. Neglecting air resistance, which velocity time graph represents its motion? Well, when you initially throw that ball upwards, it's going to leave your hand with some non-zero velocity v. So this means we've narrowed the answer down to A or B because you'll notice graphs C, D and E all start at 0 meters per second. And when the ball travels upwards, it's going to decrease in speed until it eventually reaches its highest point in motion, at which point it's going to reach 0 meters per second, i.e. it comes to a stop. And this is shown in both of these graphs. However, the ball is then going to start falling back down the way. And remember, we show a change in direction on a velocity time graph by moving between these points on the x-axis. So this means that the change in direction is shown by this graph here, which means the answer is A. And you can see the speed of the ball will increase as it falls towards the ground, but it's doing so to a negative value of velocity because it's now travelling in the opposite direction. And remember, direction and sign convention are important in higher physics. Question 3 says a block of wood slides with a constant velocity down a slope. The slope makes an angle of 30 degrees with the horizontal as shown. The mass of the block is 2.0 kilograms. So there's your 2 kilogram block moving down the slope, which has an angle of 30 degrees to the horizontal. The magnitude of the force of friction acting on the block is... Well, the first thing to notice here is these keywords, constant velocity. If the block is travelling with a constant velocity, then we must be able to say that there are balanced forces acting on the block. And that just comes from Newton's first law of motion. So that means that if we can determine the component of the weight down the slope, then we will know what the frictional force acting back up the slope is because they will be equal. So we can say the component of the weight down the slope equals the frictional force. So remember the expression for component of weight down the slope is given by W equals mg sine theta. So we can sub in our numbers now to get 2.0 for the mass times 9.8 for the gravitational field strength on Earth times sine of 30 for the angle. And then putting that into your calculator should give you an answer of 9.8 newtons, which is the answer C. Question 4 says the graph shows the force which acts on an object over a time interval of 8.0 seconds. So we have a graph of force in newtons on the y-axis against time in seconds on the x-axis. Then says the momentum gained by the object during this 8 seconds is... Well, remember, momentum gained is another way of saying change in momentum. And you should also remember that change in momentum is equal to impulse. So this question is essentially just asking you to calculate the impulse from this force time graph. So remember, to do that, we can use this expression, impulse equals the area under the force time graph. So we need to split the area under this line into shapes that we can calculate the area of. So we've already got a rectangle here, but let's split up this one to have another rectangle and a triangle. And I'm just going to label these areas as 1, 2 and 3. Just so we can keep ourselves right. So remember, the area for a rectangle is given by length times breadth, so we have length times breadth plus length times breadth for the two rectangles, plus the area of the triangle here, which is a half times base times height, and we can then plug in the numbers. So for the first rectangle, we have length times breadth, which is 4.0 times 4, and then for the second rectangle, we have the same because it goes from 4.0 to 8.0, so the length there is still 4.0, and the breadth of that is again 4, so again 4.0 times 4. And then for the triangle, we have a half times the base, so the base goes from 4.0 to 8.0, so again that's 4.0. The height goes from 4 up to 10, which is 6, so that's times by 6 there. So putting that into your calculator should give you an answer of 44 kilogram meters per second, which is the answer C. Question 5 says a planet orbits a star at a distance of 3.0 times 10 to the 9 meters. The star exerts a gravitational force of 1.6 times 10 to the 27 newtons on the planet. The mass of the star is 6.0 times 10 to the 30 kilograms. The mass of the planet is... Well, notice how we're given a gravitational force, a distance and a mass, and we're asked to calculate the mass of a planet. So you should be thinking that we're going to use Newton's law of universal gravitation here, which has the equation F equals gms mp over r squared. Now usually you might see this written as g m1 m2 over r squared, but I've just labelled them ms for the star and mp for the planet. So let's sub in our numbers and try and find what mp is for the planet. So we have F is 1.6 times 10 to the 27 equals 6.67 times 10 to the minus 11 for the universal constant of gravitation g. Remember that is a constant on your data sheet, times by the mass of the star, which was 6.0 times 10 to the 30, times the mass of the planet, divided by the distance squared. So that's the 3.0 times 10 to the 9 squared. So what I would do first is the 3.0 times 10 to the 9 squared, and then multiply that by this term here, 1.6 times 10 to the 27. And then I would simplify the numerator here, and then to find MP, I would divide the number I had on the left by that numerator number there, in order to get MP equals 3.6 times 10 to the 25 kilograms. And remember to do the squared term when you're putting that into your calculator. So that gives me the answer C in this case. Question 6 says a car horn emits a sound with a constant frequency of 405 Hz. The car is travelling away from a student at 28.0 meters per second. The speed of sound in air is 335 meters per second. The frequency of the sound from the horn heard by the student is... Well, this is a question on the Doppler effect, and we're asked to find the frequency of the sound heard by the observer. So we're going to use the equation FO equals Fs times V over V plus Vs. And you'll see that I've used a plus in the denominator because the car is travelling away from the student. So remember, the trick to remember which sign to use in the denominator is towards is take away and away is add. So the car is travelling away, so we're going to add in the denominator rather than subtract. So let's plug in our values to get what FO is. So we have Fs, the frequency of the sound source is 405 Hz, times 335 divided by 335 plus 28.0. And putting that into your calculator should give you an answer of 373.76 Hz, which we can round up to be approximately 374 Hz. So you'll see that gives the answer B. Question 7 says the graphs show how the radiation per unit surface area R varies with the wavelength lambda of the emitted radiation for two stars P and Q. So we have R in some units and then wavelength in micrometers, and we've got a curve for star P and a curve for star Q. Now you'll notice the shape of these curves are similar, but one is taller than the other. It then says a student makes the following conclusions based on the information in the graph. Statement 1 says star P is hotter than star Q. Statement 2 says star P emits more radiation per unit surface area than star Q. And statement 3, the peak intensity of the radiation from star Q is at a shorter wavelength than that from star P. Which of these statements is or are correct? Well, let's look at each statement in turn and decide which ones are true or false. So statement 1, star P is hotter than star Q. Well, looking back at the diagram, you might remember that these black body radiation curves can tell us about surface temperature, and the way they do that is from the height of the peak. So the bigger the peak, the higher the surface temperature of the star. So that means that in this case, star Q is actually at a greater temperature than star P. So we can say that statement 1, that star P is hotter than star Q, is false. Statement 2, star P emits more radiation per unit surface area than star Q. Well, looking back at the diagram, the radiation per unit surface area is going to be given by the area under each curve. So you can see that star Q has more area under the curve, whereas star P has a smaller area under the curve. And that means that star Q is going to emit more radiation per unit surface area than star P. So again, the statement that star P emits a more radiation per unit surface area than star Q is false. And lastly, the peak intensity of the radiation from star Q is at a shorter wavelength than that from star P. Well, looking back at the diagram again, we can see the peak wavelength for star P occurs at this point here, whereas the peak wavelength for star Q occurs at this point here. And you can see that this is actually slightly to the left than this peak, which means that the peak for star Q is at a shorter wavelength. So this means that this statement is true. So we have statement 3 is the only correct one, 3 only, which is the answer C. Question 8 says one type of hadron consists of 2 down quarks and 1 up quark. the charge on a down quark is minus a third, and the charge on an up quark is plus 2/3. Which row in the table shows the charge and type for this hadron? Well, firstly, let's find the total charge. So we have 2 down quarks and 1 up quark, and we're given the charge on each. So we can write that the charge is equal to minus a third plus 2/3, which will cancel each other out to give a charge of 0. So this means we're left with either answer A or answer D. But now we just need to decide whether we're dealing with a baryon or a meson, and remember in this case the hadron has 3 quarks, so it must be a baryon. And that's because baryons are made up of 3 quarks, whereas mesons are made up of 2 quarks, namely a quark-antiquark pair. So this means our answer is A. Question 9 says a student makes the following statements about subnuclear particles. Statement 1 says the force-mediating particles are bosons. Statement 2 says gluons are the mediating particles of the strong force. And lastly, statement 3, photons are the mediating particles of the electromagnetic force. Which of these statements is or are correct? So let's look through each statement in turn and decide which ones are true and which ones are false. So the first one, the force-mediating particles are bosons. That is true, and remember that comes from the diagram of the Standard Model, where the 4 force-mediating particles, the gluon, photon, W and Z bosons, and the hypothetical graviton, they are all bosons. Statement 2, gluons are the mediating particles of the strong force. That is true, and the way I like to remember that is that gluon sounds like glue, and the strong force is responsible for holding protons and neutrons together in the nucleus of an atom, and you could think about glue as being a strong adhesive, so gluons links with the strong force. And lastly, photons are the mediating particles of the electromagnetic force. Well, that is also true, and the way I like to remember that one is from the word electromagnetic. Remember, electromagnetic radiation is basically just light, and photons are particles of light. So that means all 3 statements are true here, which means the answer is E. Question 10 says the last 2 changes in a radioactive decay series are shown below. A bismuth nucleus emits a beta particle and its product, a polonium nucleus, emits an alpha particle. So we have bismuth undergoing a beta decay to create polonium, and then polonium undergoes an alpha decay to create lead. It then says which numbers are represented by P, Q, R and S. Well, for this question, because we've only got the mass number and atomic number for the final element in this decay series, then we need to start at the end and work backwards. So if we think about polonium undergoing an alpha decay here, remember an alpha decay will subtract 4 from the mass number and subtract 2 from the atomic number. So that means that R must decay by 4 to get to 208. So to get from 208 back the way to R, then we need to add 4. So we end up with 212 for that number. Similarly for the atomic number, we said that's going to decrease from 2. So S needs to decrease by 2 to get to 82. So to work back the way from 82 to S, we need to add 2, so we go from 82 to 84. And now we need to do the same thinking about a beta decay. So if bismuth undergoes a beta decay, then remember a beta decay is going to cause the mass number, the upper number, to be unchanged, whereas the atomic number is going to increase by 1. And the reason for that, remember, is that a beta decay is a neutron converting into a proton, so therefore the proton number is going to increase by 1. So if Q is going to increase by 1 to S, then that means working backwards, it needs to decrease by 1. So we end up with 212, the unchanged mass number there, and we end up with 83 for the atomic number. So that means in order of P, Q, R and S, I'm looking for 212, 83 and 212, 84. So I'm looking down here, 212 and 83, 212 and 84, which is the answer D. Moving on to question 11, it says the table below shows the threshold frequency of radiation for photoelectric emission for some metals. So we have sodium, potassium and zinc and their threshold frequency in hertz. So we have 4.4 times 10 to the 14 hertz, 5.4 times 10 to the 14 hertz and 6.9 times 10 to the 14 hertz. Then says radiation of frequency 6.3 times 10 to the 14 hertz is instant on the surface of each of the metals. Photoelectric emission occurs from sodium only, zinc only, potassium only, sodium and potassium only, or zinc and potassium only. And in order to answer this, you just need to be aware that the frequency of the instant radiation must be greater than the threshold frequency for photoelectric emission to occur. So the frequency of the instant radiation here needs to be greater than these values of threshold frequency in order to cause photoelectrons to be emitted from the metal surface. So we can see that this number is bigger than sodium threshold frequency and also the potassium threshold frequency, but it's actually smaller than the zinc threshold frequency. So that means no photoelectrons will be emitted from zinc, but photoelectric emission will occur for sodium and potassium, which gives us the answer D. Question 12 says radiation of frequency 9 times 10 to the 15 Hz is instant on a clean metal surface. the maximum kinetic energy of a photoelectron ejected from this surface is 5.70 times 10 to the minus 18 joules. The work function of the metal is... Well, because we're dealing with maximum kinetic energy here and work function, we're going to use the equation for the maximum kinetic energy of an ejected electron, which is Ek equals hf minus hf naught. And notice how we're asked for the work function, and the work function is given by this whole term hf naught here. Now, because we don't know what the instant photon energy is, hf, we need to work this out using the instant frequency. So we're going to plug in the values that we're given, which includes the maximum kinetic energy, 5.7 times 10 to the minus 18 joules. So there we have our value, 5.7 times 10 to the minus 18 is equal to the 6.63 times 10 to the minus 34 for Planck's constant h, which you'll find on the datasheet, times 9 times 10 to the 15 hertz, which was the instant frequency, minus the work function hf naught, which we're trying to find. So we could add hf naught to both sides there so that it becomes positive, and then I would do this in your calculator and subtract this value from it to get hf naught equals 2.67 times 10 to the minus 19 joules, which is answer A. Question 13 says a ray of monochromatic light is instant on a grating as shown. So you can see the monochromatic light comes in, hits the grating, and splits into this sort of triangle shape with the first order maximum and first order maximum there, and this gives a full angle of 36 degrees here. It then says the wavelength of the light is 633 nanometers. The separation of the slits in the grating is... Well, we're going to be using the grating equation here for diffraction, which is d sine theta equals m lambda, and the separation of the slits is given by the symbol d, so we want to find what d is. So let's sub in what we know here. We're trying to find d, and that's times by sine 18. Now notice how I've used 18 for my angle theta and not 36, and the reason I've used 18 and not 36 here for my angle theta is because remember theta is defined as the angle from the central maximum to whatever maximum you're talking about. So here we're dealing with the first order maximum, so my angle is going to be half of this 36, which is 18 degrees. And this is equal to 1 for m, because we're dealing with the first order maximum, times 633 times 10 to the minus 9, which is my wavelength in nanometers converted into meters. So 1 times this is simply going to be the wavelength here, divided by sine of 18, which will give us a value for d of 2.05 times 10 to the minus 6 meters, which is answer C. Question 14 says light travels from glass into air. Which row in the table shows what happens to the speed, frequency and wavelength of the light as it travels from glass into air? Well, notice how glass is a more dense material than air, so the light is going from a more dense material into a less dense material. And remember, when this happens, the speed of the light will increase, so we're dealing with either D or E as our answer here. The frequency will stay the same, because remember, frequency of the light will always stay the same no matter what material it's in, and the wavelength of the light will do the same as the speed, so it's going to increase. So that means my answer here is E. Question 15 says the irradiance of light from a point source is 32 watts per meter squared at a distance of 4.0 meters from the source. The irradiance of the light at a distance of 16 meters from the source is... Well, we're going to use our relationship here for irradiance in terms of the distance from a point source. So we have I1d1 squared equals I2d2 squared, and we're trying to find the irradiance at a distance of 16 meters. So let's say we're trying to find the final irradiance I2, and we know all the other values. So we can plug in our numbers to get 32 for the initial irradiance times 4.0 squared for the initial distance is equal to I2 times 16 squared, which is the final distance. And plugging in our numbers and rearranging for I2, we get a value of 2.0 watts per meter squared, which is the answer C. And just a quick check there is to see that the distance has been increased from the point source, so we expect the irradiance to decrease, which it has. Question 16 says part of the energy level diagram for an atom is shown. X and Y represent two possible electron transitions. So there's X going from E2 to E1, and there's Y going from E2 to E0. Then says a student makes the following statements about transitions X and Y. Statement 1 says transition Y produces photons of higher frequency than transition X. Statement 2, transition X produces photons of longer wavelength than transition Y. And lastly, statement 3, when an electron is in the energy level E0, the atom is ionized. Which of these statements is or are correct? Well, let's look through each statement and decide which are true and which are false. So statement 1, transition Y produces photons of higher frequency than transition X. Well, looking back at the diagram, remember change in energy delta E is proportional to the frequency F. So the bigger the change in energy, the bigger the frequency. So this means that transition Y, which does have the bigger energy difference, will produce photons of a higher frequency. So statement 1 is true. Statement 2, transition X produces photons of longer wavelength than transition Y. Well, looking back at the diagram, remember the relationship between wavelength and frequency is an inversely proportional one, which means the bigger one is, the smaller the other one is. So if we're talking about transition X having a longer wavelength here, a longer wavelength will correspond to a shorter frequency. And a shorter frequency, remember, if frequency is directly proportional to the change in energy, a shorter frequency will mean a smaller energy change. And you'll see that transition X here does have a smaller energy difference here, so that means that this second statement is also true. Lastly, statement 3, when an electron is in the energy level E0, the atom is ionized. Well, looking back at the diagram, this is the energy level E0, but remember, for an electron to be ionized, it needs to be in the highest energy level, because remember, ionization is the addition or removal of an electron from an atom. So in order to remove the electron from the atom, it needs to be near the surface of the atom, where the highest energy levels will be. So therefore, we can say this third statement is false, which means 1 and 2 are correct only, which means the answer is B. Question 17 says the output of a signal generator is connected to the input of an oscilloscope. The trace produced on the screen of the oscilloscope is shown. So we've got lots of waves here on the oscilloscope screen, and we've got each box representing a division here. It says the time-based control of the oscilloscope is set at 2 milliseconds per division, and the Y-gain control of the oscilloscope is set at 4 millivolts per division. It then says which row in the table shows the frequency and peak voltage of the output of the signal generator. Well, let's find the peak voltage first of all, which remember uses the Y-gain setting on the oscilloscope. So the Y-gain controls 4 millivolts per division, and remember, for the peak voltage we need to count how many divisions make up the amplitude of the wave. So if we count up the amplitude from the axis to the crest here, we've got 1, 2, 3 boxes or 3 divisions, which means to find my peak voltage I can do 3 divisions times the 4 millivolts per division, which was the setting on the Y-gain, and you'll see that the divisions will cancel out because we have divisions divided by divisions, and this leaves us with 3 times 4 millivolts, which is 12 millivolts. And that means the answer is either going to be A or D here, so we can eliminate B, C and E. And then to find the frequency, remember we need to find the period first. So looking back at the diagram, we use the time-based setting, which is 2 milliseconds per division, and remember we deal with the x-axis or the horizontal plane on the oscilloscope trace for the period, and we count how many boxes or divisions make up one wavelength. So going from the start all the way up, all the way down and back to the start, you'll see that only takes up one division. So that means for my period t, I can write t equals 1 division times 2 milliseconds per division. Again, the divisions will cancel out, and I'm left with 1 times 2 milliseconds, which is 2 milliseconds. And I'm going to rewrite this in terms of seconds because that's going to help me in a moment with the frequency. So let's rewrite this as 2 times 10 to the minus 3 seconds. Now to find the frequency, we use the relationship between frequency and period. So we have t equals 1 over f, and let's rearrange for the frequency f to get f equals 1 over t. And we can plug in the numbers to get 1 over 2 times 10 to the minus 3, and putting that into your calculator should give an answer of 500 Hz. So we're now looking at D as being our final answer here. Question 18 says a potential divider circuit is set up as shown. So we've got a supply voltage of 12 volts and 2 resistors in series. So we've got 3 kilo ohm resistor and a 7 kilo ohm resistor. It then says the potential difference across the 7 kilo ohm resistor is. Well, remember, for a potential divider circuit, it helps to label these resistors. And I'm going to start by labeling them from the bottom up. So we've got number 1 here and number 2 here. And then I'm going to use the relationship for potential dividers when the supply voltage is known, because we know that is 12 volts. So because I'm trying to find the potential difference across number 1, I'm going to call that V1 equals R1 over R1 plus R2 times Vs. And then we can sub in the values, and I'm going to convert from kilo ohms into ohms for both. So we have 7,000 over 7,000 plus 3,000 times 12, where 12 was the supply voltage. And if you put that into your calculator, you should get an answer of 8.4 volts, which is the option D in this case. Moving on, question 19 says a circuit is set up as shown. So you've got a 12 volts EMF next to a 4.0 ohm internal resistance, and then you've got a variable resistor in series with an ammeter. It says the resistance of the variable resistor is increased and corresponding readings on the ammeter are recorded. So we've got resistance in ohms and then current in amps. It then says these results show that as the resistance of the variable resistor increases, the power dissipated in the variable resistor increases, decreases, remains constant, decreases and then increases, or increases and then decreases. Well, looking back at the table of information that we were given the resistance and the current, and we want to find the power dissipated. So thinking about our power equations, we're going to use the one relating power, current and resistance, which is P equals I squared R. And we're going to use this equation for each column in our table here in order to see what happens as the resistance increases. So let's start off with the first column, which we'll use subscript 1 for. So we'll say P1 equals I1 squared R1, which is just P equals I squared R with little subscripts to keep us right. So from the table, we have 2.0 squared times 2.0, which gives us an answer of 8 watts. For the second column, we have P2 equals I2 squared times R2, which is 1.5 squared times 4.0, which is 9 watts. And then for P3, we have P3 equals I3 squared times R3, which if we plug in the numbers gives 1.2 squared times 6.0, which gives us 8.6 watts. And then for the fourth column, we have P4 equals I4 squared times R4. Plugging in the numbers, we get 1.0 squared times 8.0, and putting that into your calculator gives us 8 watts. So you can see that as we increase the resistance of the variable resistor, the power increases, but then it decreases again. So that gives us the answer of E. Lastly, question 20 says a 20 microfarad capacitor is connected to a 12 volt DC supply. The maximum charge stored in the capacitor is? Well, firstly, when the capacitor is fully charged, the potential difference across it is going to equal the 12 volts from the supply. So we can use the relationship between charge, potential difference and capacitance, which is C equals Q over V. And we're trying to find Q here, so I'm going to rearrange it as Q equals CV. And substituting in the numbers gives us 20 microfarads, which is 20 times 10 to the minus 6 times the 12, which if you put into your calculator gives an answer of 2.4 times 10 to the minus 4 coulombs, which gives us the answer of B. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.